Modern air combat is a relentless, high-speed ecosystem. It operates thousands of feet above the Earth through a network of highly coordinated machines. But look closely at any modern Air Force, and you will find a massive taxonomy of over 20 distinct aircraft classifications in active use today. This overwhelming variety highlights a core operational dilemma for defense analysts and tactical simulation players alike. Do you invest in a single-purpose airframe built for absolute supremacy in one task? Or do you save money and logistical strain with a multi-role platform that handles a bit of everything? To decode this arsenal, this matrix maps these classifications. The x-axis plots mission flexibility. The y-axis plots strategic impact. Notice the extremes. An airframe cannot occupy both maximum specialization and versatility. The better engineered for one task, the worse it becomes at everything else. Today, we are stripping away the defense contractor marketing hype to map exactly how these different platforms fit together in real-world strategy. Understanding the trade-offs within this matrix is the only accurate way to evaluate a military fleet's true operational lethality and its actual survival rate. We begin in the air-to-air domain. Before ground operations can safely launch, a military force must achieve air superiority, the baseline requirement of clearing the skies of enemy threats. For decades, the purest tool for this job was the interceptor. These jets are engineered around two uncompromising metrics: raw climb rate and straight-line speed, ensuring they reach incoming enemy aircraft as fast as physics allow. But optimizing an airframe to intercept incoming bombers in a straight dash comes with a severe trade-off. By prioritizing pure speed, designers sacrifice tight dogfighting maneuverability and entirely eliminate ground attack utility. An alternative approach to dominance is the stealth fighter, which prioritizes avoiding radar detection entirely rather than simply outrunning the enemy. To achieve invisibility, stealth airframes rely on highly specific geometric shapes. The harsh, flat surfaces and sharp angles you see here are specifically designed to deflect incoming radar waves away from the enemy receiver, drastically reducing the aircraft's radar cross-section. The trade-off here is heavily logistical. Radar-absorbent materials require massive, constant maintenance. Furthermore, to remain stealthy, all weapons must be stored internally, which severely limits the total payload capacity. Contrast both of those highly specialized jets with the multi-role fighter. This platform is built to consolidate air combat, ground attack, and reconnaissance into a single, highly efficient supply chain. Because they are not constrained by stealth requirements, multi-role fighters utilize external hardpoints. They can carry a massive, diverse weapons loadout on external wing pylons, allowing ground crews to swap payloads based on the specific mission. Dominating the sky requires a commander to choose exactly what they value most: invisible precision, sheer speed, or logistical adaptability. No single jet possesses all three. Shifting to the air-to-ground domain, the environment becomes radically more hazardous. Operating close to the Earth exposes aircraft to treacherous terrain and dense anti-air fire. This is where close air support, or CAS, classifications operate. These aircraft fly at low altitudes to deliver precise firepower in direct, continuous coordination with frontline infantry. To survive near the ground, a fixed-wing CAS aircraft requires immense durability. They feature heavy armor plating, a massive nose-mounted gun, and a rugged, straight-wing design that allows them to fly slow and stable over the battlefield. The alternative to fixed-wing CAS is the attack helicopter. Its rotary wing design gives it unique maneuverability, allowing it to hover and navigate extreme, tight environments where airplanes simply cannot fly. To eliminate heavily armored targets, these helicopters carry a highly modular arsenal. This typically features a chin-mounted chain gun linked directly to the pilot's helmet, alongside heavy side-mounted rocket pods. But all CAS platforms share a brutal trade-off. Operating low and slow makes them highly vulnerable to ground fire and shoulder-launched anti-aircraft missiles. At the exact opposite end of the ground attack spectrum is the strategic bomber. Instead of supporting troops on the front line, these are utilized for deep infrastructure strikes far beyond contested borders. Carrying a payload heavy enough to level a factory over intercontinental distances dictates the physical design. They require a massive, elongated fuselage and large, swept wings engineered for high-speed, long-duration flight.
The cost of that scale is a massive radar signature. A traditional bomber is easily tracked, meaning it requires significant fighter escorts to survive anywhere near contested airspace. A modern solution to these risks is the Unmanned Combat Aerial Vehicle, or UCAV. UCAVs are drones designed for combat missions. By removing the pilot from the aircraft, commanders execute high-risk strike scenarios without potential casualties, though they trade that physical safety for a susceptibility to electronic jamming. Building an effective ground strike capability forces a strict calculation. You must constantly balance the survivability of your pilots against the required payload size and the depth of the target. Let's move to the third domain, support aircraft. Kinetic fighters get the glory, but support planes actually provide the highest strategic return on investment. These non-combat force multipliers dictate the actual outcome of modern conflicts. The centerpiece is the AWACS, or Airborne Early Warning and Control Platform. Think of it as a flying command center that manages the entire battle space from above. You can identify an AWACS by the massive rotating radar dome mounted on top of the fuselage. This array detects incoming threats over vast distances, guaranteeing friendly fighters a crucial first-look advantage. The trade-off is that emitting that much electromagnetic energy makes the AWACS highly visible to enemy sensors. They're high-value targets that require a constant, dedicated defensive screen. Next is the aerial refueling tanker. Its sole purpose is to supply fuel mid-flight, exponentially extending the loiter time and strike range of the combat fleet. Mid-air refueling requires two aircraft flying in close formation, while a mechanical boom connects them. It is an act of extreme precision that leaves both planes entirely vulnerable. Tankers are slow and completely defenseless. If an enemy shoots one down, the fighters relying on it quickly run out of fuel, making the tanker the single biggest logistical failure point in the sky. Finally, electronic warfare, or EW aircraft, specialize in disruption. By jamming enemy communications and blinding surface-to-air missile sites, they carve out safe corridors for strike packages to pass through. The ultimate irony of modern warfare is this: the platforms that dictate who controls the airspace are often entirely unarmed. Bringing these three domains together leaves commanders and tactical gamers with one ultimate question: how do you choose the exact right tool for the job? We map operational goals through a cascading decision tree, starting with the primary strategic objective and splitting into two distinct philosophies: fleet efficiency and precision dominance. If you operate under strict constraints, you follow the fleet efficiency branch. Here, the data points to multirole fighters and UCAVs. Consolidating supply chains and training, these versatile platforms adequately cover 80%. But both of these paths rely on a mandatory foundation: transport aircraft. Without heavy lifters moving troops and supplies, the entire system collapses before a jet takes off. Sustaining an active airbase requires massive logistical capacity. That heavy lifting falls squarely on the broad wings and vast cargo holds of large-scale turboprop transports. True aerial superiority is never achieved by trying to buy a single perfect platform. It is achieved by strategically blending these specialized classifications together, using the strengths of one platform to completely offset the inherent vulnerabilities of another.